In this lesson, we'll focus our attention to understanding how finite state machines are utilized in order for us to provide the state changes that occur within our data path for a processor. And so you want to keep in mind that the finite state machine is used to represent the number of states that are possible for a given data path. So in this example, we have S1, S2, and S3, and these represent the various state changes that can occur within a data path. We have the arrows that are utilized in order to represent appropriate transitions that can occur between states. And so at an abstract level, this is utilized in order to represent sequential circuit logic, with the main purpose of being able to capture desired behaviors within a logical circuit. And so the states that we have represented here refer to appropriate corresponding physical states within a sequential logical circuit. You'll want to keep in mind that we can characterize this by denoting that we have an input to represent an external trigger that will cause a change in state behavior. And then the output is utilized in order to generate the transition from one state to the next. So in this example, we have an input that is going into, if we start at state 1, we have an input that feeds into state 2 that represents a transition from S1 to S2. Correspondingly, we have a transition from S2 to S3, as well as transition from S3 back to S1. And so in general, this provides us with a mechanism for understanding how the design of a data path can interconnect. So now we can understand the various components that represent the logic for a data path. And we can also incorporate how these effects are incorporated with the register and other interconnection components, such as buses. So here let's represent the data path that can be visible based on an appropriate garage door scenario. And in essence, we all know that a garage door is likely to have two states, and that is going to be a up state and a down state. And so in an up state, we can assume that the garage door is open. In a down state, we can assume that the garage door is down or closed. And the transition between the two states represent the garage moving from being open to being closed, or from up to down, and then also from down to being back open or up. And so within this, we consider that the input into an appropriate state would be a person pressing the garage clicker. And this can be used to denote a change in state. And so these outputs represent appropriate control signals that are used to determine whether the garage motor will force the garage to go up, or it'll force the garage to go down. And so we have appropriate transitions that are labeled 0 and 1. And these transitions respond to that there are no appropriate clicker action that is done. So this means that there is no change in state. And so we also have appropriate transitions that are denoted 4, 2, and 3. These transitions correspond to the garage clicker being pushed, and that forms a transition. So the transition that we see for state 2 is going to represent the output in which we trigger the motor uh, to bring the garage up. And so this transition goes from the garage being down to the garage slowly coming up, and then it finally is in the up position. Transition 3 provides for a state change from the garage being up to transitioning to down. So represents a logical design for the sequential circuit giving these state transitions. So how exactly could we represent this logic using a sequential circuit? We can use this by incorporating either a synchronous or asynchronous state changes. So with this state transition, we've been able to synchronize with the clock edge in order to produce the appropriate transition. So the sequential circuit is going to just provide a bit of combinational logic that we can utilize in order to form how the circuit is implemented. With this, we have appropriate corresponding inputs into the combinational logic via the clicker, as well as the output, which controls whether we'll have a up control in which the garage motor knows to bring the garage up, or a down control, which denotes whether we need to bring the garage down. And so keeping this in mind, we can denote the various outputs that are represented. This is done by denoting that for the down output is going to be the current state and clicker. The up output is going to be current state, prime, and clicker. And then the next state is going to be the current state and the clicker, or the current state, prime, and clicker. And so with utilizing the truth table, we're able to denote how these transitions occur. And so essentially what we have here is a representation for the output given the next state. And this is again synonymous with an appropriate truth table to represent those transitions from one state to the next. And so some things that we want to keep in mind is we can describe the combinational logic as Boolean expressions, circuits, truth tables. So what if we could replace a combinational circuit with a hardware truth table? So instead of turning a truth table into circuitry, we can just put the truth table into hardware. And so the way that we can do this is by making use of ROM, or read-only memory, in order to mimic a truth table that could be used in a circuit. And so if we were to take into consideration, if you have 72 controls in our data path, then we would have 72 bits in our output. And so there are a few steps that we can keep in mind to do this. We can create a state transition table, decide how many flip-flops we need and what kind, and use the flip-flop excitation table to determine the next steps for implementation. So in order for us to do this, we can have an appropriate truth table in which we replace the circuitry with within our read-only memory. And so this will represent our truth table where we have our output, our down output, and our up output. and appropriate correspondence to whether that will cause a transition into next state. And so this could be represented as 0, 0, and 0, 1, 1, 0, and 1, 1 logically. And so thus far, we've talked about a number of different components that are required for our microprocessor implementation and design. We went over the basics of logic and design, both combinational and sequential, elements of the data path, which include appropriate registers and register file. And so make sure that you have a good understanding of how a register is utilized and what is the purpose of the register file. We've talked about the purpose of the ALU, how multiplexers and decoders come into the circuit design. We've discussed appropriate considerations for finite state machines, as well as the clock and clock width. And so these are considerations that we've focused upon. And in this regard, we've talked about machine organization as it relates to the data path and control. And so we can further extract those components into having machine organization be associated with appropriate control mechanisms, and also machine organizations appropriated with appropriate data path mechanisms. And so it is important to keep into considerations the type of instructions that we have when we're working with our LC 2200 instruction set. So we've discussed our various types of instructions, our R-type instructions, I-type instructions, the J-type instructions, and our O-type instructions. And so it's important to keep in mind with each of these instructions, what is the addressing mode and what does it refer to? So you want to keep in mind that this is going to provide us a mechanism to understand how we can appropriately calculate the memory address for those instructions based off of the operand available. And so with an R-type instruction, it's going to be based off of the register. I-type instructions can be PC relative, base plus offset, or immediate. We have our J-type instructions, which are going to be register-based. And then we also have halt, which is not necessarily represented. And so now that we have an appropriate data path, we'll also need to figure out something else. And so what exactly do we need now that we've constructed our data path? Well, what is contained in our data path? The CPU consists of that data path, but it also will consist of something else that we need. And that is going to be something that is going to maintain the flow of things, and that is going to be our control unit. And the control unit is is almost is like the conductor in our data path. It will basically oversee how things are or how things are orchestrated electronically. So if we were to take a look at how a control unit is utilized, we'll have to keep in mind that for every clock signal, we have to make sure that there is an advancement in the registers to the next state. And this can be specified by appropriate output. And so that same clock can also be used to specify edge trigger storage elements in our data path. So we want to make sure that all of our appropriate load signals that are coming out of our read-only memory serve as masks for the clock signal. And this allows for appropriate determination of other elements that are required. And so it provides for calculations for next state, or if we need to go back to the start based on the clock cycle. In our next lesson, we will focus more in detail on understanding read-only memory and how it is appropriately represented.